The problem with history is not what we don't know, it's what we think we already understand. Because some discoveries refuse to stay inside the timeline they're given. Because scattered across caves, tombs, coastlines, and ancient cities are objects that should not exist where they do. Tools made by extinct humans with unexpected precision. Materials engineered thousands of years before science could explain them. Technologies that worked reliably, were used for centuries, and then disappeared completely. These are 5 real discoveries. Deep inside Denisova Cave in Siberia, archaeologists uncovered a finely crafted bone sewing needle that immediately challenged long-standing assumptions about early human behavior. The object was unmistakably functional, shaped with care and polished smooth through repeated use. Near one end, a small circular eye had been drilled cleanly into the bone, a detail that alone required a level of precision and control far beyond what was traditionally associated with prehistoric toolmaking. When researchers dated the needle, they were forced to reconsider the entire context of its existence. The artifact was between 40 and 50,000 years old. The implications became even more unsettling when scientists identified who made it. The needle was attributed not to modern Homo sapiens, but to Denisovans, an extinct human species known primarily from fragments of bone and genetic evidence recovered from the same cave. Denisovans were long thought to have lived relatively simple lives, producing basic stone tools and leaving behind little evidence of complex cultural behavior. Yet this needle told a very different story. Creating a sewing needle is not a trivial task. Bone is fragile and prone to cracking, especially when drilled. Producing an eye small enough to pass thread without breaking the material requires careful planning, steady hands, and specialized tools capable of controlled rotation and pressure. The smooth polish along the needle's surface suggests it was used repeatedly, not as an experiment or symbolic object, but as part of everyday life. This points directly to the production of tailored clothing, a technological leap previously believed to belong exclusively to modern humans. In the harsh environment of Ice Age Siberia, clothing was not optional. It had to be fitted, layered, and durable enough to withstand extreme cold. Sewing makes that possible, but it also implies something more abstract. It suggests design, repair, and improvement over time. Knowledge had to be taught, techniques refined, and mistakes corrected across generations. This kind of cultural continuity requires cognitive abilities once thought to be unique to our own species. What unsettles researchers most is how abruptly this technology appears in the archaeological record. There are no earlier Denisovan needles showing a gradual learning curve, no crude attempts leading up to this level of refinement. The needle appears fully developed, as though the knowledge behind it already existed before it ever entered the ground. And beyond Denisova Cave, no comparable Denisovan artifacts have been found. Across the Mediterranean coastline, massive Roman structures still stand in places where modern engineering struggles to survive. Harbors, seawalls, and piers built more than 2,000 years ago continue to resist waves, salt, and erosion, even as nearby modern concrete cracks, corrodes, and collapses. For a long time, this was treated as a historical curiosity, but when scientists began extracting samples from these ancient structures, they realized the Romans had created something modern science did not fully understand. Roman concrete was made from a mixture of volcanic ash known as potolana, lime, and seawater. At the time, it was assumed the durability of Roman structures was simply the result of thick construction or favorable conditions, but laboratory analysis told a very different story. Unlike modern concrete, which slowly weakens when exposed to salt water, Roman marine concrete actually becomes stronger over time. When seawater seeps into the concrete, it triggers a chemical reaction that forms rare crystalline minerals, including tobermorite and philipsite. These minerals grow inside microscopic cracks, reinforcing the structure instead of degrading it. In effect, the concrete heals itself. The longer it remains in contact with seawater, the more stable it becomes. What makes this discovery so unsettling is that this process was not understood by modern engineers until the 21st century. Advanced imaging, electron microscopes, and chemical modeling were required to figure out why Roman concrete behaved this way. And yet, Roman builders were producing it reliably more than 2,000 years ago without any knowledge of crystallography, mineral chemistry, or atomic structures. They had no concept of molecules or chemical bonds, no way to observe crystal growth, no theoretical framework to explain why their concrete worked. And yet, they selected the exact materials, the correct ratios, and even the use of seawater, a choice modern engineers would later avoid because it destroys conventional concrete. Even more puzzling is that the recipe was not preserved in detail. While Roman texts mention potolana, they do not explain the precise mechanisms behind the material's performance. At some point, this knowledge disappeared. Medieval builders did not replicate it. Renaissance engineers did not recover it. Industrial-era concrete went in a completely different direction, prioritizing speed and cost over longevity. The result is a paradox. Modern infrastructure built with advanced science and industrial precision often has a lifespan measured in decades. Roman marine structures built without modern tools or theory have survived for millennia. Some are now stronger than when they were first placed in the water. Only in recent years have engineers begun experimenting with Roman-style concrete again, attempting to recreate its properties for modern use. But even now, the process is not fully mastered. Replicating the exact conditions that allowed these minerals to form naturally over centuries remains a challenge. In ancient Egypt, long before glass was understood and thousands of years before chemistry existed as a formal science, craftsmen were producing a material that should not have been possible for its time. Archaeologists uncovered small beads, amulets, and decorative objects with a bright blue-green surface, smooth, glossy, and unmistakably artificial. These objects were not carved from stone nor molded from clay. They were made from faience. Egyptian faience first appears as early as 4000 BCE at the very dawn of complex civilization. At a glance, it resembles glazed pottery, but closer examination reveals something far more unusual. Faience contains almost no clay at all. Instead, it is composed primarily of finely crushed quartz, a material that does not naturally bind or shape itself. To turn it into solid objects, ancient craftsmen had to invent an entirely different process. The quartz powder was mixed with mineral salts and binders, shaped into beads or figurines, and then heated to carefully controlled temperatures. During firing, a chemical reaction occurred. Salts migrated to the surface and fused into a glassy glaze, forming a smooth, luminous coating without the need for applied paint or slip. In other words, the object generated its own glaze from within. This process required precise control of heat, timing, and chemical composition. Too much heat and the object collapsed. Too little and the glaze never formed. The balance had to be exact, and the results were consistent enough to be reproduced across centuries, workshops, and regions. What makes this so difficult to explain is that faience is not a naturally occurring material. It is synthetic. It does not exist in nature in this form. Every bead represents a deliberate transformation of raw minerals through controlled chemical reactions. This is not accidental discovery. It is engineered behavior. Modern analysis has shown that Egyptian faience production involved complex processes such as efflorescence, cementation, and glazing techniques that require an understanding of material behavior under heat.
These are concepts that modern chemistry would not formally define until thousands of years later, yet ancient Egyptian artisans achieved the same results through experimentation and transmitted knowledge. What is most unsettling is how early this technology appears. At a time when metallurgy was still developing and writing itself was in its infancy, Egyptian craftsmen were manipulating minerals at a molecular level, creating materials with properties that stone and clay could not provide. Color stability, surface hardness, and chemical durability were all engineered outcomes. And yet, like many ancient technologies, the deeper understanding behind faience was never written down in technical terms.
During the height of the Byzantine Empire, long before gunpowder reshaped warfare, enemies approaching Constantinople encountered a weapon that appeared to defy the basic laws of nature. From the decks of Byzantine ships, streams of fire were projected across the water, igniting enemy vessels on contact. The flames did not extinguish when they hit the sea. They spread across its surface, clinging to wood, sails, and flesh, burning hotter and longer the more water was thrown on them. This weapon became known as Greek fire. Archaeological evidence points to ceramic and bronze containers, pressure vessels, and siphon-like devices designed specifically to store and deploy this incendiary substance. These were not simple fire pots or torches. They were engineered systems capable of projecting burning material at a distance, functioning as an early form of flamethrower centuries before such technology was believed to exist. Greek fire first appeared in the 7th century CE and remained in use for nearly 500 years. It played a decisive role in defending Constantinople from naval invasions, particularly during large-scale sieges where conventional weapons would have failed. Contemporary accounts describe it as unstoppable. Once deployed, there was no known way to put it out. Sand, vinegar, and cloth soaked in water all failed. Panic often spread faster than the fire itself. What makes Greek fire so difficult to explain is not just its effectiveness, but the complete disappearance of its underlying knowledge. The Byzantines treated the formula as a state secret, reportedly restricting it to a small group of trusted specialists. It was never written down in detail. No complete instructions survived. When the empire declined, the technology vanished with it. Modern chemists have attempted to reconstruct Greek fire using descriptions from historical texts. Theories suggest combinations of petroleum, resin, sulfur, quicklime, or other reactive compounds. Some mixtures can burn on water, others can ignite upon contact, but none fully replicate the reported behavior of Greek fire, especially its sustained combustion and controlled projection.